This is the fourth segment on lecture number 5 for ME 760 at the University of Waterloo. We will see in this segment what is toxicity and what is dose. In the toxicity study, we need to understand what is a dose response and what is a dose response assessment. Usually those that cause cancer, and this is a typical graphic showing a dose response for cancer, because we have no dose, no toxic being ingested or fed to animals, and a case with, let's say, a few thousand animals. Then a straight line is drawn, and we have the slope factor here, so we can multiply the dose by the slope factor, and we get the number of potential cancer cases. This graph shows a dose response for a non-cancer chemical. A human being can resist certain chemicals until one point without any health effect, and then it produces this non-linear response. So, for example, humans can ingest salt, and that's not a problem to a certain point. Beyond that point, it will go and have a response that is not necessarily linear. This is just an example. Salt response may not look like this. Toxicity threshold is a threshold where if you go beyond, then there is a problem. If you need a permit, you won't get a permit. If you are going to cause a human health impact beyond that threshold, then there is an impact. So we call that toxicity threshold levels. We define them in terms of no observed effect level, no L. So that's, for example, a non-cancer effect you can tolerate to a certain point. Beyond that, then you start observing some effect, and this is the low L, lowest observed effect level. We also have the no observed adverse effect level, because you can have some effect, but it may not be severe to be considered to be adverse. Toxicity models are type of models that are used such that we can predict what kind of impacts it will happen. Now we need these models because there are every year thousands of chemicals being developed or discovered, and we cannot do extensive toxicity studies. So, for example, to do a lethal dose that will kill 50% of the subjects, this is LD50, it costs $1,000 per chemical. However, to do a complete cancer study, it will cost at least $500,000. There are over 70,000 chemicals not analyzed, and we need then to get models that can predict what is the toxicity that it will have on humans and ecological receptors. Weight of evidence for toxicity, primary one, is very important because we actually conduct animal studies. Epidemiological is important because we do not expose on purpose toxics on humans, but there are accidents, there are leaks, there are ways where toxics will hit humans, and then these are studied using epidemiology, and we have a response to the exposure to those chemicals. We have secondary one, and this is a toxicity model, structural activity relationship, also called SAR. We have pharmacokinetic, PBPK, and we have the persistent bioaccumulation of toxic, PBT, is persistence, bioaccumulation, and toxicity. These are part of analyzing the chemicals which we will accept with more certainty, primary ones, and then secondary ones, and tertiary ones in this order. Acute exposure levels. There are many organizations defining what are the levels that people cannot be exposed, and there's not a precise agreement. There are somewhat agreement, but the levels change. And the Human Health Risk Assessment Protocol define order of priority. First, the EAEGL, ERPG, ATEL, and the TEL. Before I conclude this presentation, we need to see that for toxicity, we have mercury, which will fit, but not as a primary compound. It is emitted as elemental mercury. It goes into the atmosphere and it will have 20% is elemental in the vapor phase, and then 60% is divalent. And of the divalent as well, 20% is divalent but particle bound. So these are separation that we make in order to accommodate the mercury report to Congress in the United States. And we can see here that in the vapor phase, which is elemental, 1% is deposited, 99% is lost to the global cycle. It will fall, for example, in the oceans, and it will contaminate the tuna. So it is not on a site that we analyze. Of the vapor, 60% of the total that we emit, 68% will deposit locally, and of this, 32% is lost to the global cycle, and the particle bound phase, 36% is deposited, 64% lost to the global cycle. If you have any questions on the segment, please feel free to email.